Hello, this is Steven, and I will be going through WJEC Chemistry GCSE level Unit 2.2 Acids, Base, and Salts. In this topic, we will be investigating the reactions of acids in depth. Neutralization theory and titration concepts are introduced as well. We should all be able to write word and balance symbol equations, including ionic equation where relevant for all reactions described in this topic. Our learning objectives for today are to describe the Arrhenius model for acid and bases, to determine whether a given chemical substance is an Arrhenius acid or Arrhenius base, and to describe a Bronsted-Lewis model for acid and bases. We should all be able to identify conjugate acid and base pairs and determine whether a given chemical substance is a Bronsted acid or Bronsted base. To begin with, I will describe the Arrhenius, Bronsted-Lewis, and Lewis series of acids and bases, and briefly explain the relationship between them. I will also explain the concepts of a conjugate pair, an acid and its conjugate base, or a base and its conjugate acid. The Arrhenius theory of acids and bases. We first need to know the theory behind it. What is an acid and what is a base? So acids are substances which produce hydrogen ions in solution, while bases are substances which produce hydroxide ions in solution. The most significant difference are hydrogen and hydroxide, two different ions, but both in solution. And neutralization often happens because hydrogen ions and hydroxide ions react to produce water. And here is the chemical formula for it. Both aqueous solutions and gives off H2O as water, liquid. There's going to be limitations of this theory. For example, hydrochloric acid is neutralized by both sodium hydroxide solution and ammonia solution. In both cases, you get a colorless solution which you can crystallize to get a white salt, either sodium chloride or ammonium chloride. These are clearly very similar reactions, and here's the full chemical reactions. We got sodium hydroxide, aqueous solution plus hydrochloric acid, HCl, and it gives off sodium chloride and some water. And same case, we got ammonia, aqueous plus HCl, and this gives off ammonium chloride. In the sodium hydroxide case, hydrogen ions from the acids are reacting with hydroxide ions from the sodium hydroxide, in line with the Arrhenius theory. However, in the ammonia case, there don't appear to be any hydroxide ions. But if you look at the equation carefully, the ammonia is in the solution NH3 aqueous and reacts with water like this. Let's get my pen out. This is a reversible reaction. Like I've said, this is a reversible reaction, and in a typical dilute ammonia solution, about 99% of the ammonia remains as ammonia molecules. There are hydroxide ions there, and those react with hydrogen ions in just the same way as the hydroxide ions from the sodium hydroxide. So you can just about to justify ammonia as being a base on the Arrhenius definition. It does produce hydroxide ions in solution, but most of the reaction is going to be a direct reaction between ammonia molecules and hydrogen ions, which doesn't fit the Arrhenius definition. This same reaction also appears between ammonia gas and hydrogen chloride gas. And here's the chemical reaction. We got gas ammonia plus HCl gas and this what gives off NH4Cl. In this case, it will be a solid. There aren't any hydrogen ions or hydroxide ions in this solution because there isn't any solution. The Arrhenius theory wouldn't count this as an acid-base reaction, despite the fact that it is producing the same product as when two substances were in solution. And we will be discussing that more later on. And now I will be introducing you to Bronsted-Lewis theory of acids and bases. We will first start off with the theory, like we did last time. So what is an acid and what is a base? In this case, an acid is a proton donor and a base is a proton acceptor. A proton in this case would be a hydrogen ion. It is completely different than the theory we discussed last time. And if you want to ask, what is the relationship between the Bronsted-Lewis theory and the Arrhenius theory? Well, the answer is, the Bronsted-Lewis theory doesn't go against the Arrhenius theory in any way, it just adds to it. Hydroxide ions are still bases because they accept hydrogen ions from acid and from water. An acid produces hydrogen ions in a solution because it reacts with the water molecules by giving a proton to them. When hydrogen chloride gas dissolves in water to produce HCl, the hydrogen chloride molecules gives a proton, a hydrogen ion, to a water molecule. A coordinated bond is formed between one of the lone pairs on the oxygen and the hydrogen from the HCl. H3O plus are produced in this case, and here would be the formula. We got H2O plus HCl. This gives us the H3O plus Cl minus. When an acid in solution reacts with a base, what is actually functioning as the acid is the H3O plus. For example, a proton is transferred from an H3O plus ion to a hydroxide ion to form water. The chemical formula would be looking like this. We've got a H3O plus hydroxide ions and gives off to water. It is important to realize that whether you talk about hydrogen ions in solution H+, what you're actually talking about are the H3O minus H3O plus ions. This is no longer a problem using Bronsted-Lewis theory, whether you're talking about a reaction in solution or in the gas state. Ammonia is a base because it accepts a proton. The hydrogen becomes attached to the lone pair on the nitrogen of the ammonia via coordinate bonds. If it is in solution, the ammonia accepts a proton from a H3O plus ion. We got ammonia and gives off H4 plus and H2O. If the reaction is happening in the gas state, the ammonia accepts a proton directly from the hydrogen chloride. It's give off H4 plus and Cl minus. Either way, the ammonia acts as a base by accepting a hydrogen ions from an acid. We are back, and now I will be going through the conjugate pairs with you, as it is, I think, it is the most important part in this topic. When hydrogen chloride dissolves in water, almost 100% of it reacts with the water to produce H3O plus ions and chloride ions. We discussed it in the previous slides. Hydrogen chloride is a strong acid, and we tend to write this as one-way reaction. In fact, the reaction between HCl and water is reversible, but only to a very minor extent. Consider an acid HA and think of the reaction as being reversible. we first need to think about the forward reaction. The HA is an acid because it is donating a proton to the water. The water is a base because it is accepting a proton from the HA. But there is also a backward reaction between the H3O plus ion and the A minus ion. The H3O plus is an acid because it is donating a proton to the A minus ion. The A minus ion is a base because it is accepting a proton from the H3O plus. The reversible reaction contains two acids and two bases. We think of them in pairs, called conjugate pairs. It is a reversible reaction. When an acid HA loses a proton, it forms a base, A minus. When the base, A minus, accepts a proton back again, it obviously reforms the acid HA. So these two are a conjugate pair. If you're thinking about HA as the acid, the A minus will be its conjugate base. And if you're thinking about A minus as the base, then HA is its conjugate acid. So we got one conjugate pair, and the remaining one will be the second conjugate pair. The water and the H3O plus ions are also a conjugate pair. Thinking of water as a base, the H3O plus ions is its conjugate acid because it has an extra hydrogen ions which it can give away again. Thinking about the H3O plus ions as the acid, then water is its conjugate base. The water can accept the hydrogen ion back again and to reform the H3O plus ions. I'm going to give you another example of conjugate pairs, which hopefully will make this clear. I will now introduce you to this reaction here. Got ammonia, water, reversible reaction gives off NH4 plus and hydroxide ions. To begin with, we first need to think about the forward reaction. Ammonia is a base because it is accepting hydrogen ions from the water. The ammonium ion is its conjugate acid. It can release that hydrogen ions again to form ammonia. The water is acting as an acid, and its conjugate base is the hydroxide ions. The hydroxide ions can now accept the hydrogen ions to reform the water. So we can draw the conclusion that those two are conjugate pairs, and those two are conjugate pairs. For the backward reaction, the ammonium ion acts as an acid, and ammonia will be its conjugate base. The hydroxide ions is a base, and water is its conjugate acid. I will now introduce you to another concept. I don't know if you see these terms either in books or by your teachers, but you may possibly have noticed that in one of the last two examples, Water was acting as a base, whereas in the other one, it is acting as an acid. A substance which can act as either an acid and a base can be described by the term here. And we will discuss more of this in A level. We're back and discuss about our last concept, the Lewis theory of acids and bases. Same question. I'm going to bring back the acid and base notation. So we've done that. Sorry. Here we go. So what is an acid and base in this case? An acid in this case would be an electron pair acceptor, and a base would be an electron pair donor. And same question, what is the relationship between the Lewis theory and the Bronsted-Lewis theory? We will start off with the Lewis bases. It is easiest to see the relationship by looking at exactly what Bronsted-Lewis bases do when they accept hydrogen ions. Three Bronsted-Lewis bases we've looked at are hydroxide ions, ammonia, and water, and they are typical of all the rest. The Bronsted-Lewis theory says that they are acting as bases because they're combining the hydrogen ions. The reason they're combining with hydrogen ions is that they have lone pairs of electrons, which is what the Lewis theory says. The two are entirely consistent. So how does this extend the concept of a base? At the moment it doesn't, just looks at it from a different angle. But what about other similar reactions of ammonia or water? For example, under Lewis theory, any reaction in which the ammonia or water use their lone pairs of electrons to form a coordinate bonds would be counted as them acting as a pairs. As far as ammonia concerns, it is behaving exactly the same as when it reacts with hydrogen ions. It is usually its lone pair to form coordinate bonds. If you're going to describe it as a base in one case, it makes sense to describe it as one in the other case as well. If you look into the Lewis acid angle, Lewis acids are electron pair acceptors. For example, the BF3 is acting as the Lewis acid by accepting the nitrogen lone pairs. Under Bronsted-Lewis theory, the BF3 has nothing remotely acidic about it. This is an extension of the term acid, well beyond any common sense. What about more obvious acid and base reaction? Like for example, the reaction here. What exactly is accepting the lone pair of electrons on the nitrogen? Textbooks often write this as if ammonia is donating its lone pair to a hydrogen ion, a simple proton with no electron around it. But this is misleading. You don't usually get free hydrogen ions in chemical systems. They are so reactive that they are always attached to something else. There aren't any combined hydrogen ions in HCl. There isn't an empty orbital anywhere on the HCl, which can accept a pair of electrons. In this case, why HCl is a Lewis acid? Chlorine is more electronegative than hydrogen, and that means that the hydrogen chloride will be a polar molecule. The electrons in the hydrogen chloride bonds will be attracted towards the chlorine end, leaving the hydrogen slightly positive and chlorine slightly negative. The animation would be looking like this. The lone pair on the nitrogen of ammonia molecule is attracted to slightly positive hydrogen atoms in the HCl. As it approaches to it, the electrons in the hydrogen-chlorine bond are repelled and still further towards the chlorine. Eventually, a coordinate bond is formed between the nitrogen and the hydrogen, and the chlorine breaks away as a chlorine ion. I will now show you the animation by using the curly arrow, which hopefully makes more sense. So we've got NH3 here. We've got HCl. Gonna change a different color. 2 electrons and moving to H plus and goes to Cl. And this gives off NH4 plus and Cl minus. Got 2 electrons and chlorine as well. The whole HCl molecule is acting as a Lewis acid. It is accepting a pair of electrons from the ammonia, and in the process it breaks up. Lewis acids don't necessarily have to have an existing empty orbitals. This should be the end of this video, and to sum up, I think to make your life more easier, I'm gonna show you one last point. Because we've been discussing, I think, 3 different theories about acids and bases. Sometimes you get mixed up, I get mixed up as well. So for me, all I remember is a Lewis acid is a electron pair acceptor, and Lewis base is an electron pair donor. Acid accepting electron pair and the base donate electron pair. All you have to do is just look for how the electron works in the balanced equation. For all general purpose, just stick with the Bronsted-Lewis theory. Alright, thank you very much. I'm Steven, and stay safe, and I hope to see you soon. Thank you.